Okay, chapter 11 covers elasticity and periodic motion. We're actually just going to cover mostly just elasticity in this video. Any of the periodic motion stuff we need will, for the most part, be covered in chapter 12. So the purpose of this is to study stress, strain, and elastic deformation. We'll also define elasticity and plasticity. And then, like I said, most of the concepts of simple harmonic motion will be covered in the next chapter, chapter 12, which covers mechanical waves and sound. So really, the only thing we're covering from this chapter is actually just section 11.1. So section 11.1 is really just to sort of take a more realistic approach to forces that act on bodies. We in previous chapters idealized objects as either being just a point, and so all the mass was just at one specific point, or we considered them to be a rigid body like we did in chapters 9 and 10, meaning that they weren't able to deform as they were rotating. But so one was they weren't allowed to form, and another that they all moved together as one solid structure here. However, the reality is that objects do deform when a force is applied to one part of a body as opposed to applying a force to another part. There's always some deformation, even if it's a very, very small scale. So we're going to look at that in this chapter. So what causes an object to deform? What are some things? What is a thing? Hopefully you say that it's a force. A force causes something to deform, right? So everything comes down to forces, right? But we're not really going to be considering a point force like we have in the past, in which we have one force that if it presses on anywhere on the block, then it moves the entire block the same amount, or it has the same exact effect everywhere on that block. We really need to look at how a force is distributed now, because we need to look at how that force is going to deform an object as well as how it's going to move it. So we're not dealing with point forces anymore, but instead we're dealing with a force applied over some particular area. This force over some area is what we call stress. Stress is, in physics, we call stress, it characterizes the strength of the forces associated with either a stretch, a compression, or a twist of an object. It's expressed formally as a force per unit area, so it's some force applied over some area. Like I just said, stress is a force per unit area, so its units would then be newtons per meter squared, which is also known as a Pascal, or the abbreviation for that we use PA for Pascal. So 1 Pascal is 1 Newton per square meter. And the British units, it would be PSI, or pounds per square inch, or pounds per inches squared here, and that is the equivalent of stress in British units. There's 4 types of stresses that we'll consider in this chapter. The first one being a tensile stress. So this first one up here, we have a tensile stress, and we have opposed forces stretching this bone as she's running with a weight in her arm. This is tension is defined the same way we define tension in previous chapters, in which it's simply a pulling apart of some object. In this case, it's a pulling apart of the bone, actually. We also have shear stresses. Shear stress causes something to twist. So her spine is pushing down right here, while her leg is pushing up right here, and it's causing her hip bone right here to want to rotate, or to shear. It's causing some motion in which this is pushing down, this is pushing up, and that's trying to to shear off. We also have compressive stress, in which this is the opposite of tensile stress, because compressive stress, one thing is pushing down and the other one is pushing up, so they're trying to compress it or trying to squeeze it, so as to make it smaller. And we also have, lastly, she were to go swimming after she ran, she might dive in the water and she would experience a volume stress, in which it's really a volume stress is a compressive stress applied sort of everywhere on the entire volume, so that it decreases the volume. Imagine a compressive stress like this, and I put some more forces in here like this, and I put an infinite number of little forces, all with the same magnitude. Then I would get a volume stress on her leg there. So that's essentially what a volume stress is. So we'll look at all of these in this chapter. So these are the stresses that we'll talk about. But how do we measure the effect of this force, or actually of this stress, on the body? You might say, well, we can see how much it hurts our legs to run or something, or we can see if there's some sort of deformation of it, right? We could say, how does the body change when I put these forces on it? So in what ways can an object deform when we apply these forces or these stresses to it? Well, we have a few ways. The ways we'll talk about in this chapter are: it can be stretched, it can be compressed, or it can be twisted. Same things we were just talking about a minute ago. So the description of this deformation is what we call strain. So that is the description of the deformation that occurs due to the stress. So stress is the cause of the deformation. Strain is the description of the deformation. Sort of like force is the cause of acceleration, and then we have equations, the kinematic equations to describe our motion, right? So it's sort of like the stress is the cause and the strain is the effect. And you might think about grab something stretchable next to you, and like rubber band or something like that, and you pull on it, and the harder you pull, the more it stretches, right? And in general, if we take the stress and we divide it by the strain, we say that we have our stress here, how much force per unit area we're putting into something, and divide it by how much it stretches. This is more or less a constant. And well, in some regions of the stress-strain relationship in this way. And as long as this follows Hooke's law, which we saw a special case of that with springs earlier, as long as it follows Hooke's law, the relationship, or this ratio of stress to strain, will be a constant. So that's basically the ratio of stress to strain. We can physically think of as, well, the more I pull on something, the more it stretches, or the more I push on something, the more it compresses, right? So stresses can be due to a tension or a compression, a shearing, or they can act on the entire body, same as that figure we discussed a moment ago. These are the different stresses that we'll have in this chapter. So a body undergoing a tension force, and tension here is defined the same way we've previously defined tension, which we just have a point apart of something. If a body is undergoing that tension force, we say that it experiences a tensile stress. Tension is tensile, and it also experiences a tensile strain. So it's important you have to say, well, there's some stress on an object, but what kind of stress is there? Is it a tensile stress? Is it trying to be pulled apart? Or is it a compressive stress? Or is it a shear stress or whatever? So we define this particular type of stress in which it's trying to be pulled apart as a tensile stress and a tensile strain. So if we have this bar in tension here, we see that there's a force perpendicular to the surface here pulling out like this, and then there's another force pulling out like this. Then this is going to cause a pulling apart of it, right? And if we were to cut the bar in half, we could see all these other little forces, and we'll assume that they're evenly distributed. So there's many little forces here distributed over the entire area. This would be a tensile stress because it's trying to be pulled apart. If we then talk about the tensile strain, well, tensile strain should be how that tensile stress affects the object, right? So how, if I'm pulling something apart, it would stretch, right? So we have the tensile stress here is really just a measure of how far the object stretches. It's this delta L. That's really what sort of dictates the tensile strain. I think I said tensile stress a minute ago, but this is the tensile strain is defined as how far it will stretch. And we actually define this as a ratio of how far it stretches to its original length. So this delta L divided by L naught, which is just the original length of the object. So again, it's just a ratio of how much longer it got versus how long it already was. It will express it as a percentage later on. So that takes care of tensile stresses. If we have a body undergoing a compressive force or a squeeze, if you will, some sort of compression, then we say that experiences a compressive stress and a compressive strain. So some figures for that one. Here we have a cross-sectional area here, just the same, pretty much the same definition we had for tensile stress and strain, except now we have both of the forces are pushing inward on the object, right? So now it is trying to be squeezed together, right? It's being compressed, and so if we were to chop it down the middle here, we'd see, okay, we have a bunch of forces pushing on it back that are all evenly distributed, and this force here, and it's trying to squeeze this piece together, right? So then if we talk about the compressive strain, well, that's just how this compressive stress affects the rod, right? And so just like we defined tensile strain as the change in length, we'll actually define the compressive strain as a change in length as well. So they're actually the same definition more or less for both of them. If I push on both ends of this, then we have, I push right here and push right here, then it's going to have the effect of making this rod shorter here, right? We have some original length L naught and then some change in that length after we apply our compressive stresses, and the compressive strain is just it's defined as the change in that length divided by the original length, again expressed as a ratio or later as a percentage. And the compressive stress is the perpendicular force divided by this area. It's a force per unit area, right? So just to put some equations up here for these, the magnitude of the tensile stress or compressive stress are actually defined the same way, just like I just said. The only difference is the direction of the force, so that it either pulls apart or pushes it together. So stress is defined as the perpendicular force, and this is the force perpendicular to the area or the surface that it acts on. So the stress is the perpendicular force divided by that area that it acts on, and that's the definition of the stress. The units for it are, well, this is newtons and this is square meters, so we have newtons per meter squared or pascals, and this works for either tensile or compressive. And since you really have two directions for both of them, we don't really give stress a direction. The magnitude of the tensile strain or compressive strain are also defined with the same equation, and they're just a ratio of the elongation or the compression of an object to its original length, just so like we saw on those previous figures. So strain is defined as the change in the length divided by the original length, or we'd say delta L divided by L naught. And because this is a ratio of lengths, right, it's meters over meters, it's a unitless measure, so we don't need to worry about units on that. We do, however, need to be careful about direction when we're talking about strain, because if we're talking about a tensile strain, then the rod or body or object or whatever is getting longer, right? So we would actually call that a positive delta L when we have tensile strain. If we have compressive strain, though, we need to say, well, the object is getting shorter, right? So we would actually consider delta L to be a negative if we're considering a compressive strain. So that's our sign convention for these. Stress, we don't have to worry about sign convention. Stress is just the stress, regardless if it's tensile or compressive. Strain, however, if it's getting longer, then it's a positive strain. And if it's getting shorter, then it's a negative strain, which sort of makes sense in here. If my L naught is greater than my L, then this would be a negative value anyway, right? So it would naturally work out just by doing the arithmetic there. So the amount, you might say, well, how much does something actually stretch or compress, right? And that depends on the object. If I take some rubber or rubber band and I try to pull it apart, then it doesn't take a whole lot of force to pull it apart. But if I take a piece of steel and I try to pull it apart, then I certainly can't, do that with my bare hands, right? I need a lot more force or a lot more stress in order to pull a piece of steel apart. So the amount a body stretches or compresses, or we'd say the amount of tensile strain or the amount of compressive strain depends on the material of the body and the material of the object. So we can rewrite this Hooke's law constant that we saw before, in which we had the stress divided by strain. Remember back a few 10 minutes ago or so, we had tensile stress divided by tensile strain was roughly a constant, right? So if we rewrite that constant, which came from Hooke's law, this is the one which we had this Hooke's law constant. We said that stress over strain was a constant. Then we'll rewrite this in terms of the stress and strain, and we'll call this actually Young's modulus, named after somebody whose last name was Young. And we can define this. Now, this isn't a constant for all materials, but it's a constant for each material, right? So we can define Young's modulus for many different materials here. But anyways, Young's modulus is this, which looks maybe a little bit daunting, but it's really not much at all. All it is the tensile stress divided by the tensile strain, or it's the compressive stress divided by compressive strain. It's just that Hooke's law constant we had before of stress over strain equals some constant value. And that's exactly what this is. This is simply the stress, tensile or compressive. So it's the perpendicular force divided by the area. This is the definition of stress, and this is the definition of strain. So it's simply stress divided by strain. Or algebraically moving these around, we have it's the original length divided by its area times the perpendicular force divided by the change in length. This is just an algebraic manipulation. If we manipulate it further, we can actually find a more interesting relationship in which we can find the perpendicular force if we're given a value of y, given a value of Young's modulus. This is analogous to if we consider a delta L, the amount something stretches. This is analogous to Hooke's law, which we saw before, which we say the force in the x direction is equal to the displacement times some constant of proportionality, right? So delta L is our displacement here, and the constant of proportionality is Young's modulus times the area divided by the original length. Because the amount it stretches is going to be dependent on the amount of material there is to stretch, right? So it's dependent on the length. It's also dependent on the area, because that's how we'll get our force, and also on Young's modulus, which depends on the material here. So let me just give you a few values of Young's modulus, just so you can put things in perspective. So we have table 11.1 from your book gives several values of Young's modulus. So you see aluminum is 0.7 times 10 to the 11th pascals, so newtons per meter squared, and brass is slightly higher. Copper is even higher still. We have iron, steel, and tungsten is much higher actually, right? About 5 times as high as aluminum. So remember that this is a relationship, or Young's modulus is a ratio of the stress to the strain. So basically, the higher the value, the more force we need to put into it in order to stretch it, right? The more force we need to apply in order to stretch something a given distance. A lot of materials have the same value for both compression and tension. All of these have the same value for compression as well as tension, but there are some that do not have the same value of y, of Young's modulus, for both compression and tension. Concrete is a good example of a material that doesn't. Concrete is very good in compression, but horrible in tension. You can pull concrete apart relatively easily. Now that we've talked about the stresses and strains, both in tensile as well as compressive stresses and strains, let's extend this. Actually, we'll go ahead and jump into three-dimensional analyses here. So if you were to dive underwater, you would experience a compressive force everywhere that would be uniform, which would ultimately result in a decrease in volume. If you dive, then you might know that as you go down deeper and deeper, if you're wearing a wetsuit, then that wetsuit compresses. So as you go deeper, your buoyancy is actually decreased. Your wetsuit becomes thinner and thinner at a deeper depth. This is because of the compressive forces that are acting on you as you go down. The forces that a fluid exerts on a body are always perpendicular. This is important. It's important now, but it'd be very important when we get into chapter 13 material. When we talk about fluid mechanics, to understand that the forces are always perpendicular on a submerged object. Otherwise, if they weren't perpendicular, we would end up with some net force, and the result of that would be that the body would move one direction or another, right? So the forces that a fluid exerts are always perpendicular to the body itself. So every face on the body has some perpendicular force on it. Pressure is then defined as this perpendicular force divided by the area on which it acts. So again, we have some force being applied over some area, and this is the definition of pressure. So just a little figure here. We have this object is down here, has some face right here. The forces acting on this are perpendicular to this face, and the pressure is defined as a force applied by this water, by this fluid, divided by its area. So when we define that as a pressure, we can also say that pressure is the perpendicular force divided by the area, which is also Newton per meter squared or pascals. Then we can algebraically just solve that and say that force must then be the pressure times the area, right? So the force here is actually the pressure times the area. Pressure times area is our perpendicular force. The reason we call it a delta area in this picture is because the area will be changing, as we'll see when it's compressed. But main thing that we take away from this is pressure is the force divided by area, perpendicular force divided by area, and so we can solve for this perpendicular force is the pressure times the area. Now you notice that the units of pressure are newtons per meter squared or pascals, and so we see that pressure has the same units as stress. And so actually pressure is the same thing as volume stress. So we simply can define, just like we had a tensile stress and a volume stress, or a tensile stress and a compressive stress, we now have a volume stress, which is actually called pressure. Pressure is a scalar quantity, and it doesn't have any direction other than the fact that it's the force that creates it is always perpendicular to the surface, but the pressure itself has no direction. So the volume stress is pressure. The volume strain, based off of the things that we've done for tensile strain and compressive strain, the volume strain would probably just be a ratio of the change in volume to the original volume, right? So it's simply the same relationship that we had before, in which we have our change in volume divided by original volume. Essentially the same relationship we had for tensile strain and compressive strain. So we have here volume strain is delta V over V naught, which is again is unitless because we have cubic meters divided by cubic meters, and we see that just a little schematic here, the perpendicular forces all come in to act over some area, which creates a pressure, and then they move this box in. This was the original outline of the box here, and it moves it into some smaller volume here. The pressure compresses all the sides of it and makes it a smaller volume. So we have the volume stress is the pressure, or actually the volume stress is the change in pressure, and the volume strain then is the ratio of the change in volume to the original volume. From this, we can go ahead and define that same Hooke's law constant proportionality ratio that we had before, that we called it Young's modulus for elongation or compression. For volume stress and volume strain, we call it the bulk modulus. So it's a bulk of material. It's some volume of material, a bulk, right? So we call this the bulk modulus B, and we define it the same way we define Young's modulus, in which it's simply our stress divided by the strain, right? So we have the stress is a change in pressure, and the strain is a change in volume divided by original volume. So the units here again are pascals, because this strain is unitless and the stress is in pascals. So we have the bulk modulus is negative delta P over delta V over V naught. This is the stress divided by the strain. So some values for the bulk modulus were given in table 11.2 in your book, just to show you how some of these materials react to a volumetric pressure change or a volume stress. Now remember again that the bulk modulus is a ratio of stress to strain. So the higher the bulk modulus, the more pressure there is required to compress the object, right? So you can see again sort of a lot of similarities, similar trend that we saw for Young's modulus. We see that tungsten has the highest bulk modulus, brass has much lower, glass has the lowest, aluminum lower again still. So there's the bulk modulus defined, very similar to Young's modulus. And this is, again, constant within a certain region, which we'll talk about later. It's constant for various materials. It's not constant across all materials, but for a particular material, this ratio of stress to strain is constant. So now let's talk about the last type of stress and strain that we said we were going to talk about, and that's shear stress and shear strain. Right now, or up to this point, everything that we've been concerned with has been the perpendicular forces. Always been a force that's perpendicular to the surface. Either I was pulling perpendicularly, or I was pushing perpendicularly, or I was submerged, so all my forces act perpendicular. But what happens if we add in a parallel force? Because after all, we know that we can break forces into vectors, right? If I know what happens when I have a perpendicular force, and I know what happens when I have a parallel force, every other direction is just some combination of these two, right? So what happens here, imagine we have a big stack of paper and we slide it unevenly. We push on the top portion of it, and we don't push at all on the bottom. Then you might say, well, we get motion on one side of it, or maybe the top half of it, relative to the other side, right? Or maybe a deck of cards, get a deck of cards and push it over, then you'd see that the top cards would move much more than the bottom cards, right? So we get a figure that looks something like this. We have here, this is maybe our deck of cards here. There's some frictional force keeping this bottom from moving, and we apply a force parallel to this surface up here. It's not being applied perpendicularly here, but it's being applied parallel here. And this one is also being applied parallel, and it results in sort of pushing this over a little bit, right? So we have this sort of leaning effect. And so we can define the shear stress as this parallel force divided by the area. So very similar to our definition for the tensile, compressive, and volume stress. The only difference here is that shear stress acts in the parallel direction. And then shear strain, we'll need to, I'll talk about this in a minute actually, but we'll need to talk about how the object moves relative to itself, really. So the parallel force is called the shear stress, and the resulting deformation of the shear stress is called the shear strain. So shearing is the one that makes an object twist or rotate or deform in some sort of rotational manner. So shear stress is defined as the parallel force tangent to a material surface, right? So shear stress is right here. That's our parallel force divided by the area over which it acts, right? This is, and of course, if we're talking about the parallel force, then the area which it acts isn't this area anymore. This would have been the area for a perpendicular force, right? The area in which it acts for a shear force, we're actually talking about this area, because this is the area it's acting if it's parallel, right? So it's a little bit different area here. So our shear stress here is parallel force divided by this area right there. The shear strain then is defined as the ratio of the displacement in x to the transverse direction h. So what do we mean by that? We mean how much this part right here displaces. It's a ratio of this to how high it is. So this would be its height here, h, which actually is given right here. It has some height h, and then it displaces at the point the parallel force is applied, or at this surface right here. Then that surface displaces some distance x. So the strain is, again, it's a ratio. It's a ratio of the distance it displaces versus the height of the object here. Instead of it being a ratio of how much it stretches versus how long it was originally, we say it's how much it moves over versus how high it is. So we can define this in terms of an angle as well, this angle phi, and so we can say the shear strain is actually the tangent of phi, this angle right here. Then we can also, just like we defined Young's modulus and we defined a bulk modulus, we can also define a shear modulus, which we use S for the shear modulus, and that's the same thing. It's simply our shear stress divided by our shear strain. And so our shear stress is defined as the parallel force divided by the area, and remember, it's this area that it applies to, this area over here. So it's that parallel force divided by this area. That's our shear stress divided by our shear strain, which is the ratio of this displacement to the original height. So here's our stress divided by our strain, or algebraically manipulating that, we get it's the height over the area times the parallel force over this horizontal displacement at the top, or it all comes down to force parallel divided by area all over this angle phi. These are all simply algebraic manipulations of in themselves. So just a bunch of different ways to write the shear modulus. The last thing that I want to talk about before we end this section is plasticity and elasticity. Now, we talked about Hooke's law. We talked about this relationship between stress and strain being a constant, right? That's actually how we define all our moduli, right? The Young's modulus, the bulk modulus, and the shear modulus are all defined based off of this stress divided by strain being some constant, right? Well, that only works if the object follows Hooke's law. So that this Young's modulus, the bulk modulus, and the shear modulus actually only work and this region here where our strain is, and this varies from object to object or material to material, but the stress is, I'm sorry, not the stress, but the strain is relatively small. It's about less than or equal to 1% of, or less than or equal to 1%. Remember I said we would define the strain in terms of percentage because it's simply a ratio of the change in length to the original length. And as long as this strain is very small, then Hooke's law is obeyed. And if Hooke's law is obeyed, then we say that it exhibits elastic behavior. And so elastic behavior meaning that if I pull it, then it stretches back. And more specifically, this is a Hooke's law is obeyed up to this point right here, right? So this means that the relationship is linear, that stress divided by strain constant works, right? This slope right here is a constant over this region from the origin up to point A. There is still some region in which Hooke's law is no longer obeyed. It's no longer linear, but it does exhibit elastic behavior. So it will, if you were to stretch it to this point, it will go back to its original position after you release the stress. That's what it means to be elastic. Elastic is that if we remove the stress, the object returns to its original shape here. So there's a region here in which Hooke's law works, and then there's a region here that Hooke's law doesn't work, but both regions are still elastic. Now, if we go further with it, if we continue the stress, the effects are sort of unpredictable, and more importantly, they're not reversible, they're irreversible. After we get past this point B right here, the material exhibits a plastic behavior. So by plastic, we mean that we can stretch it, but just like you pull apart a plastic, after you pull apart a plastic, the plastic stays in that shape in which you gave it, right? So once we pull it far enough, it continues to stretch much further, right? And we have to, and actually we don't need to apply nearly as much force or change in force or change in stress to get a much larger strain here, right? This is our stress over here. This is our strain. Here we have to apply a lot of stress to get a little bit of strain, a lot of force to get a little bit of deformation. Here in this region, we don't have to apply nearly as much stress, nearly as much force to get much more strain or much more deformation here. The slope here is much smaller than the slope here. But the behavior, maybe more importantly, is that after we pass a certain point, it stops becoming elastic and it starts becoming plastic. So I pull it apart and it stays in the shape that I pulled it. And even up here, and this isn't not all materials exhibit this behavior, but as I get up here, I might not even have to put more stress into it. I might be able to lay off a little bit of my stress and I still get some strain out of it. I can relax in my force a little bit, but still be able to stretch it because it's gotten so weak here. And then finally at point C, if we stretch it too far, then it may fracture or just completely break, right? So as I pull too far, just the entire thing falls apart and it breaks. So essentially what we have here is that there's a period in which Hooke's law works, and the constant, we have a constant stress versus strain ratio. Then, and also the object will return back to its undeformed shape. Then there's an area in which it'll still return to its undeformed shape, but that ratio of stress to strain is not constant anymore. And then finally we have a region in which if we pull it, if we add more stress, then it won't return to its original shape, and then we have just it's broken after that. That happens before we break it. And that takes care of everything we're going to cover in chapter 11. Chapter 12 will cover some of the stuff from chapter 11 with periodic motion and simple harmonic motion, but we'll put that in there.